Hi students, today we are going to see about electromagnetic induction and alternating current. In this we are going to see about what is electromagnetic induction, that is electric and magnetic, they are not separate, but a change of one will give other. Change of magnetic field will give electric field and change of electric field will give magnetic field, and we are going to see about the applications of these electromagnetic induction. And here you know this familiar fact that whenever electric current flows through a conductor, it produces a magnetic field around it. So that is a familiar fact. Current flows, heating effect is produced. Also if current flows, the magnetic effect is produced. From this we are going to see about what is electromagnetic induction. So it is possible to produce an electric current with the help of a magnetic field. That is, magnetic field can be used to produce electric current, and this type of induction is called electromagnetic induction, and Michael Faraday discovered this first. So he can be called as the father of electromagnetic induction, and this is about the introduction part. Next we are going to see about magnetic flux. Magnetic flux is given by the symbol phi b. What is magnetic flux? That you know, magnetic flux is the number of magnetic field lines passing through that normally, that is for a given area, what are the number of lines passing normally is called magnetic flux, and this is given by the equation phi b is equal to integral a, that is integral over a area b vector dot dA vector, and this is scalar product. So you can write this as BA cos theta, and this is integration taken over the area. And when you see this diagram, in this diagram this is slanting area, and here this is the magnetic field acting from bottom to top, and this is area vector. Area vector means this is perpendicular to this particular area, and such vector is called area vector, and the angle between the area vector and B is equal to theta. And when you see this diagram, here the area vector and magnetic field, they are along the same direction. So here theta is equal to 0. Here when you see the surface, it will be like this. Here the surface is like this, and n is the normal. And so here what is the equation now? Here theta will become 0. So cos 0 you know 1. So phi b is equal to BA, and this is magnetic flux, and the unit is Tm square, where T is the magnetic induction unit and m square is the unit of area. So when you substitute that, 1 Weber is equal to 1 Tesla meter square. So either it call magnetic flux in terms of Weber or in terms of Tesla meter square. And next we are going to see about Faraday's experiments on electromagnetic induction. He has conducted two types of experiment. First we are going to see about the first experiment. When you see this diagram, you can clearly understand. In this diagram, here C is the coil and G is the galvanometer, and here the magnet is kept here stationary. So the magnet stationary means no EMF is induced, so there is no deflection in the galvanometer. And when you see this diagram, the magnet is moved towards this coil, so an EMF is produced here. This is shown by the deflection. Here when you see this diagram, the magnet is kept stationary. So stationary means there is no deflection, so 0. So whenever, only during motion you can get EMF, or otherwise you won't get. And here in this diagram, the magnet is moved away from the coil. Now the deflection will be there, but in the opposite direction. And if you move in a higher speed, you will get higher deflection. The speed will increase the magnitude of EMF. And suppose if you move south pole towards left, then the direction of deflection will be different, that is in the opposite direction. This is the first type of experiment which shows that when the magnet is moved inside the coil, an EMF is induced. This is the first experiment. Now we are going to see about the second experiment. In this, when you see this diagram, you can understand. And here there are two coils. This is called a primary coil and this is called a secondary coil, and the primary coil is connected with a battery and a key, and the secondary coil is connected to the galvanometer. Both are kept close to each other so that the flux linked with this is always influencing this. Now when you see, when the key is here, when you see the key is closed. So when the key is closed, the current will increase. So when the current increase, there is EMF induced, and so here it is showed by the deflection. And when you see this diagram, the switch is now in the off condition, that is the switch is opened. So the switch is opened now, so the current in the coil decreases, and so the deflection will be in the opposite direction. So either by increasing current or by decreasing current, you can get an EMF. So only when there is change in the value of current, the EMF can be induced, or otherwise you won't get the EMF. This is the explanation of the second experiment. Now we are going to see about Faraday's laws of electromagnetic induction. So here this is very important point. Whenever the magnetic flux linked with the closed circuit changes, and EMF is induced, and hence the electric current flows, this current is called induced current, and the EMF is called induced EMF, and this phenomenon is called electromagnetic induction. So main thing you should know is, whenever the magnetic flux changes and EMF is induced, that is the main thing you should understand. And here in terms of magnetic flux, this is explained. So here when you see this diagram, this is the coil, and here there is a galvanometer, and here the magnet is moving towards the coil. So the magnetic flux linked is less here. When you see this diagram, the magnet is closer to the coil. Here the magnetic flux linked is more. So here the deflection is less, here the deflection is more. Similarly, when you see here the magnet is removed, but here still there is some magnetic flux linked, so there will be deflection like this. When the magnet is moved again, the flux linked with me is small, and so the deflection is also small. So the number of magnetic flux when increases, the deflection will show greater reading. So that is the explanation in terms of magnetic flux. So by seeing the diagrams, you can understand how the magnetic flux changes the EMF induced. And so here this is the explanation for the second experiment. Now here you know already, this is the primary coil, this is connected to the battery and key, and the secondary coil is connected with the galvanometer, and both are kept close to each other, and no current flows because the key is open here, so there is no deflection. But whenever you press the key, the current in the coil increases, so the magnetic flux also increases, so there will be deflection in the galvanometer. And when you see, when the key is open, now the current is going to decrease, and so the flux decreases, because here you see the number of lines are more, here the number of lines are less, which shows the current decreasing, and so the deflection will be in the opposite direction, but it shows a very small reading. This is the explanation of the second experiment. Next we are going to see about the first law and second law. First law, very easy one. Whenever the magnetic flux linked with a closed circuit changes, and EMF is induced in the circuit, that is magnetic flux linked with a closed circuit changes means an EMF is induced. And here what is the value of that induced EMF? That is equal to the time rate of change of magnetic flux linked with the circuit. You can say this in the formula. You can take this as E. E is equal to minus d phi by dt. d phi by dt is rate of change of magnetic flux, and E is the EMF. Suppose the coil has n number of turns, then the equation can be rewritten as E is equal to minus n into d phi by dt. Just you multiply this by n, and n can be taken inside. So d n phi b by dt. This n phi b is called flux linkage. Flux linkage is nothing but product of number of turns and the magnetic flux linking with each turn. So flux linkage is nothing but n phi s. Next we are going to see Lenz's law. The statement of Lenz's law is that the direction of the induced current is such that it always opposes the cause responsible for its production. So the current is induced, you know, when the change in magnetic flux produces the induced current. This induced current will always oppose the cause, will oppose the reason. That is the Lenz's law statement. So here the flux change is the cause while the induction of current is the effect. So always the effect will oppose the cause, that is the change, flux change. We shall see the first illustration. In this, here we are having magnetic field. These crosses show that the magnetic field is acting inwards, that is in this direction, and here this is the rectangular frame, and this side is movable. This side can be moved left or right, and this is the case when no current flows. And suppose what happens if the rod AB is pulled in this direction, the magnetic flux here increases. So here what happens, there will be induced magnetic field and this will be outwards, and here these red dots show that the induced magnetic field is in the outward direction. And here now in the third diagram, the rod AB is moving inward, and so here the magnetic flux decreases, and here the induced magnetic induction will be inwards, that is here cross and here there is dot, and in this case the current flows in anti-clockwise direction, here the current flows in the clockwise direction. Here actually we are increasing the magnetic flux, here we are decreasing the magnetic flux, and so the induction EMF will be different. Here the induction EMF is outwards and here the induced magnetic field is inwards, and this shows that the direction of induced EMF will always oppose the cause, that is the main thing. And next illustration 2, and here this is the coil and the magnet is moved in this direction, and here when it is brought close to each other, and suppose the north pole is brought here, this pole will attain north pole, that is this pole will become as north pole, so that the north pole and north pole repel each other, and this will oppose the motion of the magnet, that is some external force must be done to move the magnet inside the coil. Suppose if you move away from this coil, this will act as south pole, and there will be some attractive force between this, and we have to do some work to move from the coil. So it is not easy to move towards the coil or move away from the coil. So if we move also we have to do some work, and if we move away from the coil also we have to do some work, because without that work no energy can be transformed from one form to the other. So this is based on law of conservation of energy. So once again I will explain this. When the bar magnet is moved towards a coil, this will act as north pole, and so this will produce repulsive force. You have to do some work against this repulsive force, and this work is converted into mechanical energy and heat energy and electrical energy. Whereas in this case, if you move the magnet outside the coil, this will act as a south pole, and there will be some repulsive force between these two. We have to do attractive force between these two, and we have to do some work to repel, that is to overcome this attractive force. This work is converted into mechanical energy and electrical energy. So Lenz's law can be established as the law of conservation of energy, and the direction of current will always oppose the cause. Suppose on the contrary to Lenz's law, suppose induced current helps the cause responsible for its production, that is there will be without any work the magnet will move towards a coil, and so without any expense of energy it will move. So there is the production of energy without any work done, but that is not possible. So the induced current will always helps the cause is a wrong fact. The induced current helps the cause is a wrong fact, because only after doing some work we can get the energy. That energy is converted into electrical energy. So the reason of Lenz's law is, the reason of negative sign is due to Lenz's law. That is Faraday's second law. The negative sign indicates the negative sign is due to Lenz's law. Next we are going to see about Plumping's right hand rule, and here the three fingers, that is the thumb, the index finger and the middle finger, they are held mutually perpendicular to each other. Now this index finger will show the direction of field and this thumb is the direction of force. Next, the middle finger will give you the direction of current. So Fleming's right hand rule is used to find out the direction of current. So when you write this definition, the order should be the same. First index finger and then the thumb and then the middle finger will come. So you have to write according to this order, and the index finger points the direction of magnetic field, thumb indicates the direction of motion of the conductor, the middle finger will indicate the direction of the induced current. This is known as Fleming's right hand rule. Next we are going to see about motional EMF from Lorentz force, and here Lorentz force, you know, that is Lorentz force is F is equal to minus E into Vd vector cross B vector. That is when charged particles moves in a magnetic field, it produces Lorentz force. And here you consider this diagram, and in this diagram the magnetic induction is shown in the crosses, that is it will flow inwards. So it is shown by the crosses, and AB is any conductor of length L, and this conductor, if it moves with a velocity V, a force is produced and this force is called Lorentz force. So the Lorentz force equation is FB vector is equal to minus E into V vector cross B vector. That is a Lorentz force equation. And when you see this diagram, the electrons will go and move towards A when there is any, that is movement of AB, there is flow of electrons from B to A. And so here AB, the current will flow from B to A and the velocity is now V. And so in this case the Lorentz force, because of that Coulomb force is produced. Coulomb force is given by the formula Fe is equal to minus E into E vector. This is Coulomb force. The first equation is due to magnetic field and the second equation is due to electric field. So under equilibrium both of these forces are equal. So you can take it as Fb vector is equal to Fe vector. So minus E into V vector cross B vector is equal to minus E into E vector, and E get cancelled and cross product. So you will get Vb sin 90 is equal to E, or Vb is equal to E, because sin 90 you know 1. And what about potential difference? Usually potential difference is the formula V is equal to EL, that is electric field into length, and instead of E you can substitute Vb, because in that equation 4-6 you have E is equal to Vb, so V is equal to BBL. And you know here capital V is potential difference and small v is the EMF. So you can replace V by E. So now you can write this as E. So E is equal to BLV. This is very important equation. And here suppose if we take current, I is equal to E by R. This is according to Ohm's law. So instead of E can substitute BLV. So I is equal to BLV by R. So the direction of the current is always given by right hand thumb rule. So this is the motional EMF from Lorentz force. First you have to find out the equation due to Lorentz force and the equation due to Coulomb force, and equate both of them and find out what is Vb, which is equal to E, and then you substitute V is equal to EL in that. Usually the capital V represents potential difference and small v represent EMF. So substituting this you can get E is equal to BLV. So the direction of induced current is got from the right hand thumb rule, and hope you understand this derivation.